Welcome to lecture series on advanced geotechnical engineering. We are in module 3, lecture number 11 on compressibility and consolidation. So, in the previous lecture we have discussed about Barron's theory of three-dimensional consolidation, and we attempted to solve some couple of problems involving sand drains. As been discussed that now the current trend of the vertical drains is in the era of prefabricated vertical drains. So, we will try to discuss about more about the characteristics of prefabricated vertical drains, and then we will try to do some couple of problems which are with the prefabricated vertical drains. Then we will try to discuss about how these PVDs can efficiently be used in combination with vacuum consolidation, which is the upcoming research topic in advanced geotechnical engineering frontier areas. So, this is module 3, lecture 11 on compressibility and consolidation. So, we are under the theme here, methods for accelerating consolidation settlements and radial consolidation, and this is the continuation of the previous lectures. So, in the previous class we have discussed about a problem. Now, the solution will be discussed. So, in this particular slide, a problem wherein a oil tank is to be constructed on a soft clay. So, for this what has been done is that circular embankment has been constructed with a set of the sand drains spaced at a certain square pattern. So, we need to calculate the spacing of the square grid of the sand drains such that the tank is constructed, the maximum primary consolidation settlement should not exceed 20 mm. So, that means that what we have to do is that we have to calculate the final consolidation settlement, and the final consolidation settlement minus this settlement, that means that much degree of consolidation, up to that much degree of consolidation we have to have both vertical and radial to be considered. And then the given properties are that we have been given coefficient of volume compressibility and coefficient of consolidation vertical direction and in the horizontal direction, and diameter of the well has been given, and the desired degree of consolidation is also given for 90% in 6 months. So, the time required to complete achieve this target consolidation both in vertical and radial consolidation is about 90%. So, let us look into the solution. The solution runs like this. First you can calculate the so called rho c, the final consolidation settlement, and this works out to be 151 mm, wherein you are required to allow only about 20 mm settlement. So, 151 minus 2, 151.2 minus 20 divided by 151.2, you will get the desired degree of consolidation, but let us take UVR as 90% in 6 months. So, for this if UVR, if it has to happen in 6 months, and the thickness of the clay is 7 meters in a single drainage, because the bottom is actually having stiff clay, and TV is equal to 3.5 into 6 by 12, because 6 months divided by 12 converted into years, and what you get is that this in years 3.5, that is coefficient of consolidation in vertical direction, divided by 7 square. So, which is nothing but 0.0357. So, by using TV is equal to pi by 4 u by 100 whole square, we can actually calculate UV is only 19%. Now, by substituting U is equal to UVR is equal to 90% and UV is equal to 90% in Carrillo 1942 equation, wherein UR can be calculated. So, solving for UR you get 88%. Now, that means that whatever the arrangement we do with the so called the drain arrangement, we have to achieve the consolidation in this order. So, the TR is equal to TCVR by dE square. Now the dE square, the dE is nothing but in the square arrangement we have been told. So now n is equal to dE by 2 RW, or which is nothing but dE by dW is equal to RE by RW. Now here what we do is that we, by substituting this n is equal to RE by RW. So with that what we can do is that dE is equal to you can see that dE is equal to 2RE. So that is nothing but when you substitute this, what we get is that TR is equal to 6.2 into 6 by 12 divided by 4n square into 0.3 by 2 whole square. So this 0.3 by 2 is nothing but the diameter of the well divided by 2, that is in terms of diameter of the well, and n is nothing but the the ratio between the influence diameter, that is dE by dW. So with this what we have got is that TR expressed in terms of 34.4 n square has been actually obtained. Now after having obtained now in terms of n square, TR is equal to 34.4 by n square. So we have to do the trial and error method. So let us see that n is equal to 5, that means that n is equal to 5 indicates that the drains are placed very close, and with that TR is equal to 34.4 divided by 5 square, which works out to be 1.376, and which leads to 100%. When you compute for n is equal to 5, you compute Fn and n square by n square minus 1 into natural logarithm of n minus 3n square minus 1 by 4n square. Once we compute, we will get Fn, and after having obtained the value of TR, then you compute UR is equal to 1 minus e to power of or exponential to the raise minus 8 TR by Fn. Now so this works out to be 100%. That means that the desired consolidation is only radial consolidation is 88%. That means that we are on the conservative side. Now let us try another value, n is equal to 10. So with the TR is equal to 34.4 divided by 10 square, which reduces to 0.344, and now again by computing Fn and UR, and UR value, the computed value works out to be 85%, which is less than 88%. This in this order of n is equal to 10 appears to be n is equal to 10 or n is equal to 9 appears to be in order. So we can consider even n is equal to 9 or n is equal to 10. If consider n is equal to 10, then what we can do is that the spacing can be determined for a square arrangement, because we said that for square arrangement dE is equal to 1.13 s. So radius, effective radius is nothing but divided by 1.13 by 2. So with that s is equal to RE by 0.56, which is nothing but n into RW by 0.56. With that what we get is that RW is 0.3 by 2. So 10 into, because n is equal to 10, that is what we selected. If you select n is equal to 9, you will get 2.5 meters or 2.6 meter spacing. So 10 into 0.3 by 2 divided by 0.56. So with that we get a spacing of 2.67 meter. So what it says is that for the for the desired consolidation of 90% to happen in 6 months theoretically, without considering the smear effects and other aspects, it works out that the 300 mm diameter vertical drain is required at 2.7 meter center to center, or it is in the order of like 2.6 to 2.7 meter center to center distance. So in this particular problem, what we have done is that we have calculated UR from the given target UVR value, and then after having calculated UR, we try to match this with with the different assumed n values by trial and error method, n is equal to 5, n is equal to 10. So with that, the one which is actually layout or arrangement or configuration which gives the closer value to the desired UR value is actually selected, and after having obtained, so this implies that the settlement will be of the order of not more than 20 mm, when the tank is actually constructed and consolidation happens. So that this limiting or tolerable settlement is decided by the engineer in charge or the design engineer based on the requirement or conditions of the site, and also the requirements stipulated by the client. Now, in the similar lines, this problem can be solved at your end by a road embankment is constructed on top of a 9.2 meter thick layer of clay, sandwiched between silty sand at the top and dense sand at the bottom. That means that it is actually having double drainage, and the required degree of consolidation before the embankment construction is 90% within 9 months. That is with double drainage and with sand drains. But that means that UVR, vertical consolidation as well as radial consolidation, has to happen within 9 months. And for this purpose, sand drains of 450 mm diameter need to be installed in a square arrangement. So you can also consider the triangular layout and the square arrangement, and you can compare how these spacings are actually varying. So estimate the spacing of the drain. And from the laboratory test, what has been obtained is that CH is equal to 0.288 meter square per month and CV is equal to 0.187 meter square per month. So in calculating TR, the units need to be considered properly. And here in this, in addition to what has been actually asked, we also calculate for the triangular arrangement also, so that the layout of the sand drains can be compared in this problem, wherein the procedure is actually very similar. So what we need to calculate is that you need to calculate what is the for 90%, and then you need to calculate what is the vertical consolidation, and afterwards you need to calculate UR, and afterwards we need to calculate the TR, time factor, in terms of some constant divided by n square. So with that, for different values of n is equal to 5, 6, 7, 10, you can actually get what is the value which is actually closer to the desired degree of consolidation in the radial direction. And after obtaining that, you can actually calculate based on the spacing of the drain can be estimated for a given degree of consolidation, which is satisfying the desired degree of consolidation. And with that can be used for compared with square arrangement and triangular arrangement. So before looking into the details of characteristics of PVDs, we will try to look into some typical applications where suppose if you are having approach road embankments on soft clays, and one of the viable options is to if you are the load or the capacity, if the consolidation required to be accelerated during the construction of this approach embankment. So one of the alternatives is to go for the PVDs below the below the base of the reinforced soil wall. And here a typical cross section of a back to back RE wall is actually shown, wherein it actually has got a facing and a foundation pad, and the drains are actually placed along with a drainage blanket at the top. So this is one of the applications for PVDs for approach road embankments. And this is application of PVDs in ash pond dam risings. Like as we have the starter dike which is actually constructed on the by using the natural soil, and then the ash is actually filled up. So this generally happens in 3 stages or 4 stages. So in order to ensure the accelerated consolidation, and also in nowadays if that area is in the earthquake prone area, at the onset of say earthquake, the liquefaction susceptibility can be mitigated by using these PVDs in ash pond dam risings. So it actually has got 2 advantages. One is that it increases or accelerates the consolidation. So once accelerates the consolidation means the fly ash or pond ash beneath the stage 1 embankment and subsequently stage 2 embankment and stage 3 embankment will get densified, and the possibility of rise of excess pore water pressure at the onset of earthquake perturbance can be averted. So, this is one of the very novel application wherein the PVDs actually is used for mitigating liquefaction susceptibility. In fact, another application of PVDs is that in some areas where contamination flumes are there, and in order to drain out the contamination, contaminating fluid, this is one of the alternatives used to use PVDs. And also nowadays in municipal solid waste landfills, for bioreactor landfills, in order to vent the gas, these use of PVDs is actually coming out as one of the excellent options, and also collecting the gas uniformly. So, with that what will happen is that the gas collections will be uniform, and then the waste strength actually gaining will be uniform. That there has got accrued benefits as far as bioreactor landfills, the use of PVDs in bioreactor landfills is concerned. This is one of the novel application, and in addition for the PVDs are also now being used along with in silty sand and sandy soils, basically to safeguard or against the when the attenuation of liquefaction actually happens because of the sudden or catastrophic disturbance caused by earthquakes or due to some loadings like blast loadings, and these are actually proved to be very efficient and economical, and a lot of actually research is actually happening in these areas. Now, let us look into the typical details of PVD. So, prefabricated vertical drain. So, in this particular slide, what we see is a typical plan view and a cross section of a PVD, and what we see is the filter jacket, and inside is the core, and between the cores are the channels, and it is connected, it is covered by a filter jacket. So, as we said that this filter jacket is actually generally made with nonwoven geotextile, either with polypropylene or polyester or any other appropriate material, and this core which is actually made with the HDPE or polypropylene core, basically it actually has to be efficient in draining the water even under stress, even under this conditions where the stress is actually subjected. So, the rectangular cross section consisting of a synthetic geotextile jacket surrounding a plastic core, basically they are made with the PET and PP geotextiles. That is what we have just now discussed. Now, each and every component actually has got a specific function. So, if you look into this functions of the drain jacket or filter jacket which is surrounding this plastic core, is prevents the closure of the internal drain flow under lateral soil pressure. That means that when the soil pressure is exerted in the lateral direction, it prevents actually the closure of the internal drain flow under lateral soil condition, and to form a surface which allows the natural soil filter and to develop to inhibit movement of soil particles into the drain. So, it actually also helps to form a natural soil filter to develop or to inhibit movement of soil particles into the drain. So, soil filter is actually developed to inhibit the movement of soil particles into the drain. So, that is the the prime functions of the drain jacket, and the other functions of the drain core are to support the filter fabric. That means that it gives and provide the longitudinal flow paths along the drain length. So, the plastic core functions are that it provides the longitudinal flow paths along the drain length, and to provide the resistance to the longitudinal stretching as well as the buckling of the drain, to provide resistance to longitudinal stretching as well as buckling of drain. So, with the presence of the drain core, it actually resists the longitudinal stretching as well as the buckling of the drain. When we look into the quality of this PVDs, we will understand that these during the installations they have to sustain certain tensile stresses, otherwise what will happen is that the possibility of 100 mm width reduces to about 80 mm or 70 mm because of the necking formation which actually takes place. So if the necking actually occurs, very difficult to ensure the so called discharge capacities is one of the prime component which is actually is required in the design. So in this particular slide we have discussed about the two prime functions of a components. One is drain jacket, other one is drain core. Now this is the typical scheme of PVD installation. We have seen the installation at the site, in one of the sites in Navi Mumbai, wherein this is a schematic sketch is actually being shown here. So the roll is actually loaded and it is being driven with an anchor, and you can see that once it is in place here, the mandrel is actually withdrawn. So here there is an anchor is drawn. So these mandrels are actually having different shapes. They have got rectangular mandrel surrounding the drain, or the rhombus shape mandrels. So basically these mandrels have been designed from the construction practice point of view to reduce the so called smearing effect or disturbance during the installation of these prefabricated vertical drains. So here a typical installation, stage wise installation of PVD is actually shown schematically. So in this particular slide, typical anchor bars which are actually used to keep the PVD in place during the installation. So in this particular photograph, what has been shown is that how the anchor rod of 12 mm diameter and with a overlap of about 150 mm, and here these staple pins are used to hold this in place to form a loop like this, and then this anchor bar which is actually having 200 mm. That means that if 100 mm is the PVD breadth, then twice the breadth is actually used, and you can see that this is placed here, and then this is the mandrel, this is the rectangular mandrel. What we are seeing is rectangular mandrel. In this case this is with the anchor plate arrangement, wherein where the plate will be there, and then this is actually there is a possibility that this anchor plate can cause more disturbance as it is being pushed into the soil, and it actually has got the tendency of developing the large smear zones, and this is actually schematically shown in the photograph here, how the anchor plate is actually attached along with the PVD. So this is the anchor bar and this is the anchor plate. Now as we have discussed that these PVDs actually they come in the rolls. So we also have to take enough precautions to have the continuity, in the sense that if when we actually have rolls which are attached, so there should be continuity. Otherwise what will happen is that the flow channels will not be continuous, and then there is a possibility that that discontinuity, when it occurs at number of location, drains will not be efficient. So in order to avoid these things, for the typical type 1 and type 2 drain, the field practice actually says is that this is the existing running roll, and then the filter can be peeled out like this, and then it can be inserted. So minimum 300 mm lap, and then these are actually placed again so that the soil will not enter, and this is spliced back here. So here in this first step, open the filter backward for about 300 mm of the old drain as shown here. Then afterwards insert the opened core into the new drain to ensure the smooth overlap, and fold back the filter, secure the opening by tape and staple actually as shown here. So you have to secure so that again soil particles will not enter through this particular zone, because we have discussed that one of the functions here, if the soil particles enter into the drainage channels, the efficiency of the drains will get affected. And in the second type drain type 2, insert the new drain into the old drain and overlap the length should be again here also 300 mm, and secure the opening by the tape and strip. So almost it is same, it is universally it is adopted. And also while testing the quality, we also have to see how the joint is actually having effect on the tensile load strain behavior, because if that overlapping is not adequate, there is a possibility that the tensile stress and strain behavior will get affected. In a way, there is possibility that we develops failure and then discontinuity. So because of that, there is a possibility that the functionality of the desired functionality of the system may not be achieved. Now let us look into certain prefabricated vertical drain properties. There are three basic things. One is that equivalent diameter of a drain. So this was actually discussed in the previous lecture. The conventional theory of consolidation with vertical drains assumes that the vertical drains are circular in cross section. So conventional theory of the consolidation with vertical drains basically assume that the vertical drains are circular in cross section. Therefore, a band shaped drain need to be converted to an equivalent circular diameter. So a band shaped or rectangular drain to be converted into a equivalent circular diameter, which implies that equivalent diameter of circular drain has the same theoretical radial drainage capacity as the band shaped drain. So the conventional theory of the consolidation with vertical drains assume that the vertical drains. So as discussed in the previous lecture, the basic theories which are actually developed are for the circular cross sections. So now these drains, the number of equations and then parameters which are there have to be accounted for the different properties of the drains. So one of the important aspect is that TW is equal to 2 into A plus B pi phi, that is for the equivalent diameter of the well. So converting the rectangular area, so equating the rectangular area, which is pi dW is nothing but the perimeter of the circular area of the well, equivalent circle is equal to the rectangular perimeter. So with that we get the radius as A plus B by pi. This is actually after Anspo 1981. And Rexner proposed that D is equal to A plus B by 2, D or dW is equal to A plus B by 2, and this was proposed based on some Farrant element analysis results. But however, the universally this is actually adopted, dW is equal to 2 into A plus B by 5. Now the filter and opening size, as we said that the filter jacket is actually made with nonwoven geotextile having certain apparent opening size and having certain mass per unit area. So the general guidance for the drain permeability is that K filter, that is the permeability of the filter jacket, has to be at least 2 times the permeability of the soil. So we know that most of the clays which are actually undergoing consolidation may permeability, let us say 10 to the power of minus 9 meter per second minimum, it actually should have 2 into 10 to the power of minus 9 meter per second, and filtration requirement is given by O95 by D85 should be less than or equal to 3. So O95 that is the opening size indicates that in the approximate largest particle that would effectively pass through the filter, and D85 indicates the diameter of the clay particles corresponding to 85% passing. So O95 by D85 less than or equal to 3, and the retention ability of the filter is given by O50 by D50 less than or equal to 24. And the filter material can also become clogged if the soil particle becomes trapped when the filter fabric structure. In this case O95 divided by D15 should be greater than or equal to 3. So clogging can be prevented if O95 is greater than or equal to 3 times the D15. So 3 to 4 times D15 if it actually is there, then the clogging can be prevented. So filter material of a filter jacket can become clogged if the soil particles become trapped within the filter fabric structure. That is, the pores which are actually there, when they are actually occupied with these soil particles, the clogging can actually get mobilized. And so, the clogging is prevented by ensuring that O95 by D15 is greater than or equal to 3. So, the general guideline for the drain permeability is that the filter should have more permeability than the soil, and the filtration requirement is given by O95 by D85 less than or equal to 3, where O95 indicates the approximate largest particle size that would effectively pass through the filter, and D85 indicates the diameter of the clay particles corresponding to 85% passing. So, the retention ability of a filter is given by O50 by D50, which is less than or equal to 24. Similarly, now another important parameter as far as the discharge capacity is concerned. So, discharge capacity is basically is the flow, volume of the flow happening through the PVD under a unit hydraulic gradient. So, the discharge capacity of the PVD is required to analyze the drain or well resistance factor. Suppose the lower the discharge capacity of the PVD, then then efficient is the consolidation effect on the consolidation performance of a PVD stabilized soil. So, in practice actually well resistance can develop due to deterioration of the drain filter, may lead to significant reduction of the cross section, and fine soil particles may pass through the filter and decrease the area available for the flow. So, that means that the channels get blocked by the soil particles. With that, what will happen, the effective area for the water to flow will get decreased, and folding of the drain due to soil settlement may result in a reduced discharge capacity. So, this we may have to note that the PVDs, which are actually flexible in nature, and when the soil is actually subjected to settlements, and these PVDs due to these two reasons. One is that the soil is subjected to settlements because of the onset of consolidation, and the second thing is that due to the presence of the lateral pressure, the drains actually subjected to so called buckling. That means that they can undergo at buckling at one location, two locations and three locations. So, even under those conditions, in the buckled conditions, it should be able to satisfy the required discharge capacity requirements. So, the discharge capacity, which is nothing but function of volume of the core and lateral earth pressure acting on drains. So, this lateral earth pressure, if wanted to be estimated, this is actually obtained nothing but Kh is equal to K naught sigma V. At a given point, if you are having a vertical effective stress, and K naught based on for a normally consolidated soil, if you look into it 1 minus sin phi. So, we are able to take it as, let us say 0.5 times sigma V is the lateral earth pressure at any point. So, the possible folding which actually can arise due to the reasons which have been explained, and the twisting of drain due to large settlement, and it can also happen buckling, or it can also undergo so called twisting, and infiltration of the fine soil particles through the filter, and the biological and chemical degradation. So, the discharge capacity of a PVD which is actually installed in the field can actually get affected with the following factors: volume of the core, lateral earth pressure acting on drain, and possible folding and bending and twisting of drain due to large settlements, and infiltration of fine soil particles through the filter, and the biological and chemical degradation. Now, this discharge capacity is given by QW is equal to Ft into Fc into FFC into Q required. So, these where Fc, Ft and Fc and FFC are the influence factors due to time, drain deformation and clogging respectively. So, these factors are that Ft, Fc and FFC multiplied by Q required. The term Q required is the theoretical discharge capacity calculated from the Barron's theory of consolidation. So, that Q required can be obtained by epsilon F into U10 into L by into phi Ch divided by 4 to H. So, where epsilon F is the final settlement of the soft soil equivalent to 25% of the length of the drain installed to the soft ground, and U10 is the 10% degree of consolidation, L is the depth of vertical drain, and CH is the horizontal coefficient of consolidation, and TH is the time factor for the radial consolidation. So, the actual discharge capacity QW is given by FT FC into FFC into Q required, and the term Q required is the theoretical discharge capacity calculated from Barron's theory of consolidation. With that, Q required is equal to epsilon F into U10 into L into pi CH divided by 4 2H, where epsilon H is the final settlement of the soft soil equivalent to 25% of the length of the drain installed in the soft ground, and U10 is the 10% degree of consolidation, L is the depth of vertical drain, CH is the horizontal coefficient of consolidation, and TH is the time factor for radial consolidation. So, if you look into this, according to after considering all the worst conditions like due to settlement, buckling, and then deformation of the drain due to lateral pressure that may occur in the field, the discharge capacity QW of the PVD could be around 500 to 800 meter cube per year. So, most of the manufacturer specified values are actually with 500 to 800 meter cube per year, even under the lateral pressure conditions, but reduce it to 100 to 300 meter cube per year, where I is equal to 1 under elevated lateral pressure. So, this is actually after. So, most of the PVDs which are commercially available, and they actually have the discharge capacity more than 100 meter cube per year. So, most of the PVDs which are actually available have got discharge capacity more than 100 meter cube per year. So, if this is there, then we can actually consider if this QW is low, then there is a possibility that it can actually get affected the drainage capability of the the PVD which has been selected and used for draining water from the soil at the onset of consolidation. So, in this particular slide, a typical summary of discharge capacities specified in the different projects is actually shown, and discharge capacity QW is defined as the volume of water per unit time that can conduct along the core of PVD in axial direction under unit hydraulic gradient. So, QW is the discharge capacity is given by Q by I, and I is the hydraulic gradient, and here you can see that the straight conditions and buckled conditions are actually prescribed here, and in the Netherlands for the length of the drain less than 10 meters or the thickness of the clay layer less than 10 meters, in straight condition it is greater than 10, and which is at the test condition is about 350 kilopascals and 30 days, and in case of buckled condition it is 7.5. Okay. Which is when it is greater than 10 meters, the straight condition actually should have 50 meter cube per actually second into 10 to the power minus 6. So, if you multiply this one with 31.536, we actually get into meter cube per year. So, you can see that even under the buckled condition for this case here, which is 7 into 30 is about 200 meter cube per year at 350 kilopascals of pressure. So, even under the buckled condition for the majority of PVDs, they actually possess the discharge capacity capacities in the range of 100 to 200 or 300 meter cube per year. So, in this particular slide, required drainage capacity as a function of PVD length and K of the soil can be seen. As the length of the drain is actually increasing, and K of the soil is say decreasing, then it can say that the discharge capacity falls down. You can see that as the length increases, definitely yes, there is an increase in the discharge capacity, but let us say that for a length of about 20 meters, this is the discharge capacity. So with increase in permeability of the soil, then the discharge capacity requirement also increases, because the larger the permeability, the more is the water is pumped into the larger the permeability of the soil, the more is the water pumped into the flow channels, and so the selected PVD has to be economical in understanding the requirement. So if you look into the liquefaction mitigation issues with the with the sand or silty sand consent, first of all the installation in these sand conditions, sandy soil conditions, a little bit can cause a worry, and because of the frictional resistance offered to the mandrel and all, mandrel of a the tool which is used for installing these PVDs, and then you can say that with the decrease in permeability, that means that there is an increase in the required target desired discharge capacity for a given length. Now as has been told that because of the this jacket is actually supported to the core at a number of locations. So the certain portion which actually will remain unsupported. So for a particular type of plastic core, and which is like this, and because of the soil it actually causes deformations. So you can see that there are certain areas actually where the necking actually takes place, and in addition to that, if these elongation conditions are actually clubbed with this thing, and then there is a possibility that it will get affected. So the reduction of the flow area caused by the deformation of the filter can be seen from this slide. So these conditions hamper the flow conditions through the flow channels, and which in a way affect the performance of a PVD installed site. So this is a typical drain with and without smear zone. Has been told that this is a condition where if you are actually having a perfect drain and the smearing ratio, that is ds by dw is equal to 1. If that is the case, that then that S is equal to 1, wherein that is called as a perfect drain. And when you are having this smear effect because of the disturbance caused by the anchor plate or the mandrel which is actually pushed along with the drain in the installation process, as it has been shown before, it can actually cause the smear, and this smear zone is actually referred here in as the disturbed soil. So the lot of actually work is actually happening to define the smeared zone, as well as it was discussed in the previous lecture. These smear zone also actually has zones like transition zone and transition zone, and then smeared zone. Completely smeared zone is actually close to the drain, and then there is a transition zone where the soil properties tending to go close towards the undisturbed soil conditions, and then there is undisturbed soil or undisturbed clay will be there. So the time required for the radial consolidation for PV drains, this is actually equation is modified by Hansbo 1981, considering the disturbance effects and drain resistance factors. So Hansbo 1981 modified for the time required to achieve the radial consolidation or horizontal consolidation, T is equal to time required to achieve UH is given by T is equal to dc square by 8ch within brackets function n and plus function s plus function r, the bracket close, into natural logarithm by into square brackets 1 by 1 minus UH, then the square brackets close. So here if you look into it, there are three factors. One is Fn, that we are aware of that, and wherein we said that for drains without any smear, and which is nothing but a function n is equal to n square by n square minus 1, natural logarithm n minus 3n square minus 1 by 4n square, and for as n is equal to dE by dW, and because this n value will be always more than 20 for PVDs. So 1 by n square is close to 0, and n square by n square minus 1 you will tend to become 1. So because of that this Fn is actually simplified as ln to the natural logarithm of n minus 3 by 4. So Fn is actually given by ln of n minus 3 by 4 or 0.75. So Fs is nothing but the factor for the soil disturbance, and wherein that this is because of the smear, and which is actually taken care like kh by ks minus 1 into natural logarithm of ds by dw. So ds by dw is also called as the smearing ratio, that is diameter of the smear zone divided by the diameter of the well, where s is equal to a smearing ratio, s dash we can say, and Fr is the factor for the drain resistance. So this is because of the the possible effects, ill effects due to the affecting of the drainage discharge capacity or drains discharge capacity. So the factor for the drain resistance is actually accounted, which is Fr is equal to Fz into L minus Z into Kh by Qw, where in this particular expression for Fr is equal to pi Z into L minus Z into Kh by Lw, where Z is the distance below the top surface of the compressible layer, and then L is the effective drain length, H for one way drainage, and if H is the thickness of the clay layer, and H for one way drainage and H by 2 for the two way drainage. In fact this when we try to simplify further, when you take for the entire length, then you get the expressions for the drain resistance factors Fr and Fr for one way drainage and two way drainage within the drain. So by looking into this, we can actually calculate the time required to achieve UH, and if you are actually having this Fr, the Fn divided by Fr, which is actually say something like less than 0.05, then the well resistance is actually can be ignored, and it actually governed by the drain spacing only. Now after having discussed the PVD characteristics and the installation issues, let us look into some couple of problems where PVDs were installed in a compressible clay layer of 10 meter thickness in a square pattern with a spacing of 2 meters, and the PVD used is 100 mm wide and 4 mm thick, and the coefficient of consolidation of clay is in the vertical as in horizontal direction, and which is actually given as 2 meter square per year and 3 meter square per year, and the boundary below the clay was impervious, and what we need to calculate is calculate the degree of the consolidation achieved in 1 year's time. So here the dimensions of PVD is given, and CH and CV are given, and here is also assumed that no smear and no well resistance need to be accounted. The solution works out like this: first estimate DE, because the layout which is actually given here is the spacing of 2 meter square pattern. So we can actually calculate DE is equal to 1.128 or 1.13 S into S is equal to 2 meters. So with that we get the effective diameter as 2.256 meters, which is nothing but 2256 mm. And dW is nothing but equivalent diameter of the well, which we have considered 2 into A plus B by pi. So which is nothing but 2 into 100 plus 4 by 3.1415, which gives 66 mm. Then you calculate Fn with a simplified version of ln n minus 0.75. So ln 2256 by 66 minus 0.75, which works out to be 2.78. Now calculate the time factor due to radial drainage, which is nothing but TCH by DE square, where T we want in 1 year's time, CH coefficient of consolidation horizontal direction is 3 divided by 2.256. 2.256 is nothing but effective diameter in the unit cell, then it is 0.589 we get. Now calculate the degree of consolidation due to radial drainage, wherein 1 minus e to power of minus 8.589 divided by 2.78, after simplification we get 82%. Now the time factor for the vertical consolidation is about TCV by H square, because it is one way drainage. So 2 into 1 divided that is CV is 2, and 1 is the time divided by 10 square, because of the single drainage is 0.02. So by using TV is equal to pi by 4 u by 100 whole square, calculate the UV, and using the Carrillo's equation you can actually calculate what is UVR. So by substituting UV is equal to 16% and UR is equal to 82%, and we can see that UVR is about 85%. So the degree of consolidation which can be achieved in 1 year time by inserting drains at 2 meter spacing of the particular PVD which is selected, it works out to be of this order. Now let us consider the same problem assuming that smearing ratio is 3, that means that this particular performance is actually affected because of the smearing ratio, and the coefficient of consolidation of the smeared soil is given as 1.5 meter square per year. So calculate the degree of consolidation achieved in 1 year's time. So here for this FSN, here it changes because wherein it actually has got the smear effect, and with that what you actually get is that the so called FSN which by taking into account of the smear effect. So the degree of consolidation due to radial drainage is actually now is instead of in the previous problem we have got like 82%. Now because of the inefficiency of the drain, because of the occurrence of the smear at the onset of installation, the degree of consolidation radial drainage works out to be 70%. So again by using that vertical consolidation, that is about what we have got in the previous problem as 16%, we can calculate now with this the UVR works out to be UVR works out to be this value is not correct, but UVR is actually reduced. So comparing the answers, it can be seen that the degree of consolidation has reduced due to smear effect, because now once you take Carrillo's equation, by substituting this you can actually calculate the correct UVR value. So comparing the answers, it can be seen that the degree of consolidation UVR has reduced due to smear effect. Now for testing these drains under straight condition or deformed conditions, several testing methods actually have been devised, and this is a particular arrangement the drain with a deformed condition. It can be seen that the flow is tested when the drain is under this type of deformed condition. So when we compare the discharge capacities of the drains with the straight and buckled condition, you can see that the buckled condition actually exhibits buckled condition actually exhibits the lower discharge capacities. So here you can see that under the pressure. So what we can see that 150 kilopascals of pressure when it is applied, the discharge capacity is around 16 to 10 to the power minus 6 meter cube per second, whereas this was actually is about 80. So that means that there is a reduction of the discharge capacity because of the straight and buckled conditions. So we have to ensure that these discharge capacities are actually adequate for suiting to the soil conditions. So all these conditions need to be considered. Similarly, this is the tensile strength of the test for the PVD. So it should note that the tensile strength should be such that it can sustain the tensile load applied during installation. So minimum 1 kilonewton is required at 10% strain, and necking actually reduces the discharge capacity. So necking should be avoided. So this is a typical constant rate elongation method testing for the combined PVD. So this is the typical tensile stress strain measured for the two typical drains. You can see that the drain 1 and drain 2, and these are the typical specifications of the PVDs which are followed in China for L less than 15 meters, L less than 25 meters and L less than 35 meters, and wherein the thicknesses 3.5, 4 mm and 4.5 mm. And you can see that the discharge capacities are about 670 and 1000 and say 1800 meter cube per year under the pressure of 300 kilopascals, and the tensile strengths are actually that is kilonewton per 10 centimeters is greater than 1 and 1.3, and tensile strength of the filter is also very important, and tensile strength of the filter in wet condition is also shown here. So, tensile strength of the filter in wet condition is actually have to be less than this one, but in the previous curve actually it was noticed that the tensile strength of the filter in the dry in wet condition is actually more than a dry condition. So, this is the circular type drain used for vacuum loading projects. So, you can see that this is a typical drain used for vacuum loading projects, which is especially when the drain is actually connected. So, this is the schematic arrangement of the vacuum flow loading system. Now, currently the lot of research is actually happening in connecting PVDs directly to the vacuum pumps, and with that what will happen is that the consolidation can be accelerated efficiently and without any preloading. So, this is a schematic sketch is actually shown here, where we have PVDs and then different components which actually has which is connected to vacuum pumps is actually shown here. So, here you can see that the PVDs are connected directly to the vacuum pump, so that the water is actually sucked into this. So, here in this particular arrangement of when we combine PVDs with the PVDs in this case, it's actually the PVDs actually have to do, in case of vacuum preloading, they have to drain the water as well as apply the suction uniformly. So, in this way this will facilitate for the better and efficient system. So, in this particular module we actually have discussed about the consolidation theories, and thereafter we actually have discussed the different types of conditions like normally consolidated and over consolidated soils, and then finally we have discussed about methods for accelerating consolidation settlements, and particularly we have discussed in depth about the vertical drains usage in accelerating consolidation. And as a forward path we can see that lot of potential is there for research in areas of with vacuum consolidation in combination with PVD, and different applications of PVDs like as I said in the bioreactor landfills or mitigating liquefaction can be explored.